All right, folks, welcome everyone. And today we are going to talk about a very interesting topic. All right, folks, this topic is about, in fact, it's one of the very powerful generative models. So this is about a very powerful generative model today. And I think one of the first very successful generative models we'll learn about. It's called variational autoencoders. Variational autoencoders have wide applications. Many of you, for example, have been using stable diffusion or some form of diffusion models. Have you guys been using it? Do you know what that is? DALIs and things like that. So if you want to start understanding how those things work, this is the place to begin. Variational autoencoders are fundamental to the ideas of that. When you put it together along with diffusion, and the diffusion comes from the theory of non-equilibrium thermodynamics. If that sounds scary, don't be scared. The ideas are quite simple, and we'll get through that. But today is going to be a little bit mathematical. I'll try to make it as unmathematical as possible, but the word variational comes from variational inference. When you take variational inference together with the concept of autoencoders, some quite magical things happen, and we are going to talk about it. In fact, you come upon a very, very powerful neural architecture, or a whole family of neural architectures. All of this come under the umbrella of variational autoencoders. So given the fact that we have limited time, we'll break our session into two parts. First is I'll review what we have done so far in autoencoders. So we can become fresh again, what we did the last time. Remember, we talked about undercomplete, overcomplete autoencoders and sparse autoencoders, denoising autoencoders, contractive autoencoders, and all of that. We'll do a review of all of that. Then I'll introduce the concept of variational autoencoders. We'll talk about the power that it brings and the many things that it makes possible. It's one of the foundational neural architectures, guys. It is used in so many places to create many powerful things. So we'll learn about that. We'll learn about some of its limitations, even though it's a much better thing than the vanilla autoencoder for many situations. And it is a generative model in the true sense. It also does come with some limitations. And then we'll talk about time permitting, and depending upon whether we can make fast enough progress, we'll talk about one of the more recent and popular variants of it, called vector quantized variational autoencoders. Does that look reasonable, guys? And I will sort of talk of the original variational autoencoder and then jump straight to a vector quantized variational autoencoder. But it's because of a limitation in time. Variational autoencoders are themselves, not just autoencoders, but variational autoencoders are literally a topic of research. You can quite literally do a PhD in it. It's a very deep topic, and there's only so much that we can go down that rabbit hole. So I'll give you a general sense of the landscape, but we'll stick to the big ideas so that you can use it in practice. Does that make sense? Okay, so with that, and I apologize, today is probably, as we move forward, some parts of it can get a little bit mathsy, but I'll try to minimize it as much as possible and instead substitute intuition for the math, right? Knowing that this is your first introduction to neural architectures. So let's go back and review what we learned so far. We learned that...
Sorry, Asif, it's not showing up on Zoom. You're not sharing your screen.
Oh, my screen is not sharing. Again.
Yes.
Any better now?
Yes.
Okay, this is better. So let's start by reviewing the autoencoders. We learned that first we thought of the classic picture of an autoencoder is something like this, that there is a bottleneck layer. These are the undercomplete autoencoders. Whenever people think of autoencoders mentally, intuitively, this is what they think of, something with a bottleneck, isn't it? In this concept, we also talked about the fact that bottlenecks are good. The bottleneck principle, one of the underlying principles in neural architecture, says that when you introduce bottlenecks in neural architectures, it forces the machine to learn meaningful representations. Very much like when you are in school and you're asked to summarize a book into an essay, let's say one-page summary, you're forced to extract and understand the core message, the core theme of the book, isn't it? So a very similar thing is done by these bottlenecks when you introduce them in neural architecture. So that was the broad idea. Now, with this broad idea, we went and we talked about the fact that when you actually do this, you have an encoder and a decoder. Encoder function converts it into this encoder function produces a latent representation. Do we remember this, guys? It produces a latent representation. This is the work of the encoder, and this is the work of a decoder. Decoder decodes the latent representation being Z. Decoder decodes it back into uh, uh, output of the same size as the same dimensionality as the input. But when it does so, you hope that it is not just the same dimensionality, it is pretty much identical. It's a close approximation of that. Do we remember that, guys? Right? So what happens is that, let's say that the encoder creates a very compressed representation, a two-dimensional representation of an image, hypothetically. And then the decoder should be able to decode that two-dimensional representation back into that image. Right? So that's the main picture. So how does it do that? We typically, the encoders are themselves multi-layered neural nets, and they go through a few layers. Usually they're feed-forward layers or they're CNNs, right? You can implement it using that. And the loss function that you use in the vanilla version of the autoencoder is just the difference between what you sent in and what you got back. Right? So suppose you sent in X and you got back X prime, then it makes sense that X prime minus X squared would be a measure of the reconstruction loss. Does it make sense, guys? Yeah, go ahead, Albert.
So that Z, does the encoder include that Z part?
No, encoder produces the Z. So the way to think about it is, okay, let me draw this out so maybe we can summarize it. The way to think about it is that X goes in and now I'll just make it, even though autoencoders can be overcomplete, but just for the sake of this, it produces a Z, which is, let's say, a representation, a vector of this dimension, right? And this gets decoder, encoder, produces this, decoder, then takes this Z, right? Or maybe I'll just represent Z. Well, Z is produces Z. Z belongs to some latent dimension D, right? Let's say that this belongs to Rn. So this is the latent vector representation belonging as a vector in the D-dimension space. And then you decode it to get X prime, which again belongs to the n-dimensional, original dimensionality. Are we together, guys? Right? This is it. And what you want to do is that you want Z to be good, to be an efficient representation. For it to be an efficient representation, even though it takes up much less space, much less dimensionality, What do you want it to do? You want it to somehow capture all the information that is there in the much larger vector X, isn't it? Somehow you want the encoder function fx, which produces z, to be so good that it somehow manages to compress all that x is into all the information that x has into a much smaller vector z, right? And then, of course, then comes the decoder part, which will be x prime is equal to the decoding of this vector, right? To back to the original dimensional space. What are the uses? For example, you can do compression. Data compression is a very obvious use. What other uses we came up with? You remember what other things you could do? Denoising you could do. How did you do denoising? One easy way to do denoising is don't send X, but instead send X plus some noise sampled from a normal distribution, right? You add that and then you send it into the autoencoder. But when it produces X prime, compare the X prime to the original, not to the input. So you basically say, I introduce the noise, but go learn what the original picture must have been, which you have never seen. Isn't that magical that you can force it to do that, right? And one way to think of the denoising autoencoder is this. Let me give you a sense of what it is. Geometrically, suppose the data really should lie along this manifold, this curve. Let's say that the data should really be along this curve. Are we together? And what you do is you are sending it data instead here, things like this. And what are you doing? You're forcing it to produce an output. You're saying that the output better be this. The output should be points in this curve. You're comparing it. You're forcing the output to converge to the underlying manifold, underlying surface that you're not showing the machine. Guys, is it making sense?
Yeah.
Right? That's what you're really doing. You're saying, hey, I'm not going to tell you what that underlying surface is where the data actually sits, but I'm going to give you data near it. You figure out that, what its real location should have been, right?
During the training, we should give that the X clue, right?
No, you don't give that. You deliberately don't give that. You said, you know what, suppose, so I'll give you an example. Suppose you want to give 5. You deliberately say 5.12, but you better produce 5.
How do you confirm that one? So it is during the training cycle, it is producing 5.
No, let's take it very simply. What you do is, it is not actually, it is fairly simple. Let's take 2-dimensional points. So these are 2-dimensional points, right? So these points I can represent with x1, x2, the 2 dimensions, any input, right? Let us say that the real input was a 2.5 and 3.7. Let's say that x is this as an example. What you do is you do x plus error term, some noise, right? Which noise is sampled from a Gaussian distribution.
Okay.
Now, what is a Gaussian? It's small perturbations around 0, isn't it? It's a bell curve centered around 0. So then what happens? This will become, so x plus will become something like a 2 point, let me say, pick a number around 2.5.
5.7. 5.2.
5.3, right? And take 3.7.
1 or 0.1.
3.65, let's say. Is that reasonable? right? Small perturbations. So now the input to the encoder, you give this as the input, right? And what happens is that it produces a Z that gets decoded and it produces an X prime. Now, whatever X prime it produces, which will have the two terms, X1 prime, X2 prime, right? What you do is now you need to find the loss. Right? You need to penalize it, the penalty term. So the traditional way of penalizing is you would compare it to what you sent in. Right? Normally you said, okay, I sent this in, and so I just need to make sure that it faithfully reproduces what I sent in. That's your normal autoencoder. Right? But what you do is you deliberately say, no, I'm going to do X1 minus this term. Right? So let me call it X noisy, right? Minus X noisy. I will do this. Now the machine never knows what the original value is. All that the machine knows is that it has some noise. Are we together? Guys, are you getting it?
Yes. Mathematically, yes, but not processing.
Yeah, so see what you're saying is that to the machine, you're saying that I'll continuously keep introducing little noise into the data. But you need to somehow come up with a noise filter. Internally, one of the things you need to do is create a noise filter, right? That essentially filters that noise. And no, how will it do that? The way to do that is it will discover, somehow it will learn, create a noise filter and say that, see, data is not all over the place. The data is along this solid yellow line. Right? So given anything, whatever thing that I get here, I just sort of assume that it is coming from a point on the line that is closest to it. Right? Even though I got this, I need to go back to this. I need to learn a way to go back to this and pick a point that is on the solid yellow line. So what I need to do is, it's a hide and seek game. They have hidden the solid yellow line. I need to go discover the solid yellow line. And whenever I'm given an input, I ignore the input. Instead, I pick the nearest point on the solid yellow line and treat that as the real input.
So in the code, okay, we are comparing with the X prime minus X noisy, so the square.
Yes.
Which is the loss.
Right.
So which is the training is to minimize the loss, which is trying to get it to 0.
Right.
So when it gets to 0, which is basically like a matching to 2.
Yeah. No. So hang on. I am saying that you don't do that.
Oh, okay.
In a normal autoencoder, you would have done that.
Yeah.
But in a denoising, you say
that original X.
Yeah, you compare it to the original X.
Okay. Okay. So that was my question.
Yeah. Okay. You are saying that unlike a normal, so a normal would have done this. It would have said, you produce this. I gave you this thing. So the logical thing is, go minimize this.
Yeah.
Right? Go minimize this in a normal autoencoder. In a denoising, you say, hey, I never told you. I never gave you. I gave you the noisy version, but I'm going to penalize you in how much you differ from what I wanted you to infer.
Yeah.
Now it makes sense. Right?
Yes. So you're doing gradient descent on the original X.
Original X, yes.
To go back to the data, are we using backpropagation?
Oh, machines always learn by backpropagation. That's assumed. Right? They always will backpropagate the gradient and learn from that.
So here, one fundamental thing I didn't understand in this encoders, like why we need to compress.
Why do we need to compress the representation? I will answer that, but would somebody like to give it a stab? Why do we need to create a bottleneck?
So I will explain it using the opposite of it. If we expand it,
then what will happen is for every input, it will create a point in that middle layer, and it will start memorizing every one of those points.
Yeah.
So, which is the opposite of what
Transitive.
we want. We want
That's
it to not memorize, and we need to generate. This.
Yeah. Yeah, good answer. So, Prashant, let me just speak. Somebody here in the audience said that, but I'll just say that. See, you choose to do that when you have a compressed representation of data, z of input, when x goes to z is equal to some compression of f in a undercomplete. So this is an undercomplete autoencoder. Then what happens is, you not only come up with you take up less space. For example, if you're transmitting signal, isn't it better that you transmit less? Prashant?
Yeah.
That is one. But more importantly, learning takes place, and that's the bottleneck principle. That Z is not just a compressed representation of X, it is somehow a better representation of X. Right?
Okay.
And how it is a better representation, you'll see right now. By the way, when I spoke of the denoising autoencoder, it is usually the opposite. Huh? It is like this. It is overcomplete. So you send X plus noise into this, and here X prime minus X, you consider the loss function, right? So when you look at overcomplete autoencoders, just as a recap, I said that, see, it is paradoxical. Why would you create an overcomplete autoencoder? Because if you create an overcomplete autoencoder, let's say that X goes in and you do it like this with a Z, so this belongs to Rn, this belongs to Rd, and if D is greater than N, there is a risk that the machine will quietly learn a trick of just copying it over. Right? One easy way that it can minimize this loss is by simply figuring out a way to copy the data from input to output. Isn't it, guys? Does it ring a bell? We could do that. The machine is clever and it could learn to do that. So one way to prevent that, there are multiple ways that you can prevent it. Some of the ways, we talked about 3 possible ways that we explored. One way was the denoising part, isn't it? Don't give it X. Instead, give it X plus perturbation of X. Let some noise introduced X. But then, so this is the denoising, is one way of doing it. The other way that you can do it is, you can do sparse autoencoder. Do you remember this, guys? Sparse autoencoder. In the sparse autoencoder, for example, you may insist that only some of the Z, so Z will come out as a vector, with a big vector, Z1, ZD. Are we together? Right? Some vector will come out. You insist that the magnitude of, you start penalizing for the size of the terms. You say that this is a penalty term. When I attach a penalty term like this, what will it do? To reduce the penalty term, the machine will start forcing down many of these values to get close to 0. Isn't it, guys? One easy way, if to the loss term, if to the reconstruction loss, I add this penalty term, then how do you minimize the loss? Right? Besides reconstruction, the other trick that the machine will learn is, hey, let's not use all of the dimensionalities of Z. Let's just suppress some of the dimensions, isn't it? And when you do that, and sometimes what people do in this sparse autoencoder, they do even more clever trick. You take Z, you produce Z is equal to Z1 all the way to ZD, but you don't consider this to be the real Z. You do one further transformation. You pick the top K by size, values, whatever the values are, pick the top K values of Z in this vector, and top K keep them, 0 the rest. As an illustration, suppose I have a vector 3, 1, 4, 7, 9. and I say top k is equal to 2. So what will this vector become? This vector will become 0, 0, 0, 7, 9. Isn't it, guys? Does this make sense? This vector becomes this. And so what you say is that for any given input, only a few of the neurons in the latent layer can get activated. The others have to produce, like we will treat them as zeros. And then we will say the decoder must decode this vector, this thing, and these things have just been cancelled out, but go back and produce the original picture, whatever it was, the original information, whatever it was. Right? That is your sparse representation. It was inspired again by neurobiology, the realization that in our brain, whenever we do the processing, whenever some activation happens, some sensory information comes, only a sparse set of neurons are activated. Are we together? The brain has trillions of neurons, isn't it? 100 trillion neurons or something like that. Like literally, I think the human brain has close to 100 trillion neurons. But every time, so for example, you're listening to me, does it mean that all 100 trillion neurons are buzzing in response? Not. Right? Only a small subset of them are responding to what you're hearing me speak. And so that inspired the sparse autoencoder. Yes.
So I understood that part. On the previous one, when you have the noise input, I'm trying to visualize how the machine, when you give the, how are you telling in the machine that the data input, what is the error and what is the actual?
You don't tell it.
So if you're just feeding, say in that example, 2.53,
yeah,
and you actually want machine to predict 2.5,
yeah,
how is machine going to
learn that? How is machine going to learn that? Yeah. Okay, see, I'll give you a simple example. See, what does the machine have to do? Suppose I give you, so let's take something very simple. Suppose this is the actual data, right? Your data is x1, this is the x2 axis, x2, x1, right? All the points that you will feed it, in reality, these are the real points, all the points on the line. Are we together? Isn't it? And what is a line described by? What is a line parameterized by? A slope? Yeah. In school, you write it mx plus b, right? Mx plus b. Let me write it in the school notation. Mx plus b. Now, in machine learning, we tend not to use mx plus b. We tend to use a little bit, one theta naught, let's say, plus theta 1 x. This is your intercept, b. And this m slope is here. Are we together? People tend to use sort of Greek letters quite a bit. For parameters of a model, they would do that. So now think about it this way, Bhavin. All you're saying is, even though you're giving these points in reality, perturbations, and you expect the machine to produce the real points, right? What is logically the machine thinking? The machine has only one task to find out. Guess what? Its real job is to find out theta naught and theta 1. Right? Because if the machine finds out this line, if the machine can reason through internally and have when we say that it is a model, it is a model of what in this situation? It has modeled the surface of the line, right? The surface of the data, which in this case happens to be just a line, isn't it? And it has learned that. If through backpropagation, it learns that line, do you realize that it has solved the problem of denoising?
Well, it could, the line intercept could be different if it's taking, say, 2.53 versus 2.5. Right? The line could be higher or lower. How do we know that?
No, because you don't give it one data point, right? You give it millions of data points sampled from this. So imagine that you're giving lots of data, lots of these points that you're taking from this. Above and below.
Okay, Yes, based on those multiple data points, what is the closest approximation?
That is it. What is the surface? What is the hypothesis that it needs to make such that in each case it produces a response that the loss function will give the least penalty on? Right? And that basically is the learning of theta naught and theta 1, the slope and intercept of the. So it will hypothesize that data is coming from a line. And if the model can hypothesize that the data is coming from a line, it pretty much is done. Because for every point, it will just ask itself, well, I got that yellow point, but in reality, what is the nearest blue point to it? Does that make sense? Right? And that is it.
So just a quick follow-up to that. So the data that you feed, this entire data set would have some noise or only some data set?
No, every data point, every point that you insert, you perturb it with noise, with Gaussian noise.
Ask if you don't do that, what happens?
If you don't do that, then your machine will just begin to copy the data over. Yeah, because if it is over complete, it will just start copying the data over.
Can you give us some real-time scenarios like in this case?
Yes, very much so. So what happens is when you create this denoising, the simplest use case is quite literally in blurry images.
Yes.
Right? Grainy images.
Blurry images is the feed. You mean that is the blurry image? It's a feed. That is the Z.
Once this model, so think about it this way, guys. This model, I train it. What does it do? Once the model has been trained, right? What can I do? Whatever the autoencoder, in this case, it will be the opposite way. It will look like this. Let's say that it looks like this, right? I have trained this model to clean up input. But tomorrow, I actually bring a blurry image, right? And just feed it without, I don't need to add noise to it. It is effectively noise added. What you're saying is, this image that I'm giving you is actually some clean image plus noise, isn't it? That's what you're saying. And what is this machine trained to do? It's trained to infer the cleaner version of the input, isn't it? And therefore, what will it produce? It will produce a nice picture of your cat.
Yeah, last week you gave that person with mask, without mask, like your iPhone face detection.
That's right.
Or any crime scene.
Yeah, and then you can use it for other aspects also, completion. So for example, you could take a picture and then you can mask out a certain region. And you can say, hey, the noise that I'm just occluding certain thing, go fill in the blanks. Right? So you could do little things, though, by the way, at this task, right, the thing that I'm going to teach you today is much more effective than just the sparse autoencoder. Right? But little bits, it will fill it in. Coffee stains, it will remove, and things like that. So that was your sparse autoencoder. The other way that you could do was that the contractive autoencoder. The contractive autoencoder is somewhat similar. It just says that if the signal changes a little bit, right, don't change the latents. Don't change the hidden representation. Why is that likely? So for example, let's take a situation. People are used to giving you a picture. You just say, hold it horizontal. But everybody is tilting it a little bit. But you do want the hidden representation to still be stable. Right? So then what you can do is that contractive autoencoders, they penalize, what do they penalize? They penalize the gradient of the loss with respect to the latent layer. Right? So gradients is the sense. What is gradient, guys? So this is a little bit of math, but I'll just give you an intuition, guys. Now, yeah, slope is one way to look at it. It's the slope. What is slope? When you say that the slope of a function is high, what it means is the function is the response is very sensitive to the input at that point. Isn't it? So suppose I have a function, any function. So imagine this function here at this point, look at this point A and look at this point B. At what point if I do small deviations, a small, let's say I go from A to this direction, right? The same amount in both the cases from A and B. Suppose I go, in which case is the Y, the response changing more? A. And where is the slope more? Where is it steeper? A, right? So remember derivative, another intuition of derivative or slope is that, or gradient is a measure of sensitivity of the thing that you're producing, for example, the loss, right, to whatever the input is with respect to you took the gradient. So, for example, if this is y and this is x, right, you're saying that at this place, small changes in x produces a significant, much bigger change in y than at position B. Are we together? And so, if you want to make sure that your input, like your latent z is somewhat insensitive to small perturbations. If x goes from x to delta x, you want that x should go, like let's say that fx should go, z is fx, right? And then let us say that you want to say that you give it the other z prime, let us say, is equal to fx plus delta x, small perturbation of x. Guys, does this delta notation make sense to you? Or I'm saying take x and make small changes to it, right? For example, you might add a noise, or you may slightly rotate it or do whatever you want to do. Now, suppose you say that I want to create an autoencoder where z is essentially the same as z prime, is almost the same as z for small perturbations. How can I make sure of that? What does this mean? You realize that z is equal to fx plus delta x, isn't it, guys? And there is something called Taylor series expansion that you may remember from calculus. It says that it is the same as what? Derivative of f with respect to x times delta x, isn't it? Sensitivity with respect to the input. Does that make sense, guys? Right. And so if you say that z prime is essentially the same as z, what you're saying is z is fx. You're saying that this is approximately the same as fx. So how is that possible? That is only possible. This is a small perturbation. You can't play around with it. How can this be true? That's when this is approximately equal to 0. Does this make sense, guys? Look at this, right? I'm stating the obvious. If this thing has to be approximately the same as fx, then the derivative has to be close to 0. Isn't it? In other words, look at this picture. If for small delta x, y value doesn't change, what is the slope here? Is it flat? It's flat here, right? That's it. So in other words, you train an autoencoder to have near zero gradient with respect to small perturbations of the z changes, almost doesn't change with respect to perturbations in x. Right? That is the contractive autoencoder. So these are the ones that we talked about last time. Guys, this is a review. I just want to get a show of hands. Is this all making sense? Right? These are your world of autoencoders. It is making sense.
So
Right?
the use case for this you said is the shaking while taking a picture.
Shaking, yeah, that's right. For example, right, or slight rotations or so forth. You don't want the latent representation to change. Right? So this is called the contractive autoencoder. And I've just introduced you to a small family of autoencoders. We can spend a long time, a whole day, talking about many, many different autoencoders, the standard autoencoders. Right? There's a vast literature and many, many PhDs have been done on this.
Last week you had told us to try out, taking an input into an autoencoder and then with feeding just one image and then see what it does.
Right.
I was wondering like which, I went to the PyTorch, I searched for autoencoders, nothing came up. I was wondering if you have any guidance on which.
No, I could do that, guys. I've given you the the code, right, to create a neural network, the universal approximator, the neural network code. So what do you need to do to create an autoencoder? Just create one network looking like this, right? Create a few layers looking like this. See, I can release you guys the solution. Maybe I should actually at this time. I was hoping that it wouldn't be necessary, but I could do that. It's very easy. Autoencoder is easy. All you do is take two neural networks. One shapes it down, one shapes it up. That's all. That's all, right? And then take the output of one and feed it as the input to the other, and treat the whole thing as a box. That's all.
On the top, you had like, you changed the numbers to 0 right, before the 7, 9.
That was the sparse in the sparse autoencoder. That was a different one. Yes, go ahead.
Could you explain why you changed it to 0?
Because we deliberately want to force it to learn sparse representations, like low dimensional representations of the data.
Like, how do you know what numbers to choose?
No, you just pick the top, the biggest, keep the biggest two and kill the rest. You can pick 2, 3, 4, whatever it is. Pick the biggest ones, and you say those directions have signals, other directions don't, and you just kill them. All right, guys. So this is a review of the last time. Any questions before we continue? Any questions, guys? Yeah. No questions. So is it clear? The final, like this is your last call to ask any more questions on the basic autoencoder, right? So this is what we did the last time, guys. And autoencoder, at the end of it, I hope you did go back and review the book. I give you this little exercise, but I can see if you, how many of you have done that problem? Feed it a tiger or feed it just one image of yourself and keep on training it and seeing what comes out. No. A few of you did that. Okay, since many of you haven't, I'll give you a little bit of time, maybe another 2-3 days, then I'll release the solution for that. Right? Then you can see, and maybe in the TAR, I'll request the TA to walk over the solution, right, and show you how it goes. Unfortunately, this is a very condensed course, so we have to count on also the TA hours to fill in some of the necessary things. Otherwise, we can't do it. I'm going to give you guys a 5-minute break, and no more than 5-minute break, and then we will start on to the new topic,